So welcome everyone to Yann LeCun's plenary lecture today. It's really my pleasure to welcome Yann. And before I'll hand the word over to him, I'll say a few words about his biography. Yann LeCun is Vice President and Chief AI Scientist at Facebook and Silver Professor at NYU, affiliated with the Grant Institute of Mathematical Sciences and the Center for Data Science. He was the founding director of Facebook AI Research and of the NYU Center for Data Science. He received an engineering diploma from École Supérieure for Electronic Engineering in Paris and a PhD from Sorbonne Université. After a postdoc in Toronto, he joined AT&T Bell Labs in 1988 and AT&T Labs in 1996 as head of image processing research. He joined NYU as a professor in 2003 and Facebook in 2013. His interests include AI, machine learning, computer perception, robotics, and computational neuroscience. He's a member of the National Academy of Engineering and the recipient of the 2018 SIAM Turing Award, together with Jeffrey Hinton and Joshua Bengio, for conceptual and engineering breakthroughs that have made deep neural networks a critical component of computing. Today, Yann will speak about the deep learning applied math connection, and I very much look forward to your talk, Yann. But before I hand over to you, let me just remind everyone that you can submit your questions in the chat or the Q&A box throughout the talk, and questions will then be handled at the end by Gitta. So with that, I hand over to you, Yann. Very much look forward to it.
Thank you very much. Thank you very much for the introduction, and thank you to Joel and the organizers for inviting me. I'm really glad that I can do this in real time. I prefer this to having to record a talk in advance. Okay, so I'm going to talk about deep learning, obviously, and I've been trying for many years to try to sort of connect the applied math community to this problem, and it didn't happen until deep learning sort of became very prominent. But now it's really happened. Okay, so as you're probably all aware, the main workhorse of machine learning and deep learning at the moment, and AI really, is supervised learning, where you train a machine with examples and you feed the machine with the correct answer. And machine learning consists essentially of minimizing an energy function or loss function, an objective function, I should say, that averaged over the training samples minimizes the error measured in some way between the output you want and the output you get. And this works amazingly well for speech recognition, for image recognition, for even translation and things of that type. But it requires a lot of samples, and it seems that humans and animals are able to learn with considerably fewer samples. So people have worked on things like transfer learning and things like this, but none of those solutions really kind of approach the efficiency that we see in humans and animals. As you probably all know, supervised learning, but also all other forms of learning generally use a form of gradient descent called stochastic gradient descent, which consists in basically having a very noisy estimate of the objective function and its gradient based on either a single sample or a small number of samples and not averaging over. So that rules out a lot of sophisticated optimization methods that people in this community, in the applied math community, have worked on for many decades. And the properties, the convergence property of stochastic gradient, of course, have been studied extensively in the context of adaptive filters, but also in the context of sort of large-scale machine learning. So this is now the workhorse, stochastic gradient descent. Nobody even considers anything else, but they do consider refinements of it where you try to exploit the structure of the objective function to find the minimum. Now, deep learning in this business is the idea of essentially building, or at least a simple form of deep learning, is the idea of building a learning system by stacking multiple layers of parameterized nonlinear functions, essentially functional modules. And it's easy to compute the gradient of the objective with respect to all the parameters in a chain like this by basically applying chain rule, as I'm sure you're all aware of. This is what in neural net and machine learning people call backpropagation. So a classical neural net is really a sequence of alternated linear and nonlinear operation. The linear operation is just a matrix multiplication, essentially, or perhaps a sparse matrix. And then the nonlinear operation is a pointwise nonlinearity, very often one of those what people call ReLU, which is really a half-wave rectifier. So it's the identity when the argument is positive and equal to 0 when the argument is negative. And by stacking linear and nonlinear operations of this type multiple times, you get a fairly powerful parameterization of a lot of, a family of a lot of useful functions. So there are theorems that show that with only 2 layers, you can approximate any function you want as close as you want. And so the question the theorists might ask is, why would you need multiple layers? And it took a very long time for some of us to convince the community that actually, indeed, multiple layers were useful. The reason being that the world is essentially compositional. So a lot of the data that we're trying to process with this, be it images or other sound or other natural signals, tend to be compositional. They have a lot of local correlations. And so if you have compositional signal, there is an advantage in sort of processing it hierarchically by sort of progressively extracting more and more abstract representations of that signal. So that's the kind of the sort of conceptual philosophical necessity for layers. There's a more immediate one, which is that the family of functions that seem to be interesting for us to learn seems to be more efficiently represented by multiple layers than by just 2 layers. Even though you can represent them with 2 layers, most functions require a ridiculously large number of nonlinearities in the middle layer. And so it's really impractical for things like, say, image or speech recognition. You really need multiple layers. And what I've been puzzled by is why it took so long for people to really sort of come to terms with this. So one reason is that people in sort of machine learning and optimization were really sort of upset by the fact that when you stack multiple layers, the objective function now becomes non-convex. And of course, there is no proof of convergence where you have a non-convex objective function. So a lot of people objected to the fact that you don't know what you're doing if you're optimizing a non-convex function. Now, experimentally, it's been known for 4 decades that there is essentially no problem of being stuck in local minima in multilayer neural nets, as long as they are bigger than necessary for the problem at hand. So if you make the network much bigger than necessary, in the end, the function may require way fewer elements than you put in your network. But if the network is much bigger than necessary, then the optimization problem becomes relatively easy, and your system never gets stuck into a local minimum because or very rarely, because the space of solutions is actually a big chunk of the overall ambient space of parameters, and it's very easy to find a local minimum. The minima are very degenerate, and so it becomes easier to find it. Now, when you tell this now to statisticians, they tell you, oh, but that's an abomination, because now you're using an enormous model with lots of parameters, and you have absolutely no evidence that your system will work outside of sample, will generalize, because it's so over-parameterized. And there, something else happened, which is a bit of a theoretical mystery and seems a bit like magic, which is that those systems, despite being widely over-parameterized, seem to generalize regardless. And so you may have neural nets with hundreds of millions, billions, even hundreds of billions of parameters, and they end up generalizing fine with way fewer training samples than they have parameters. So that's a bit of a mystery. I think there's a lot of very interesting work, theoretical work that sort of tries to explain this phenomenon in terms of some sort of implicit regularization. So it seems that when you stack linear layers, ignoring the nonlinearities for a moment, you seem to get sort of a natural reduction of the rank of the activations in the intermediate layers. There's an initial paper by Nadav Cohen and Sanjeev Arora about this, and sort of a follow-up paper by Nadav kind of showing that there's some sort of automatic rank reduction that might explain some sort of implicit regularization that occurs naturally as a consequence of gradient descent learning. There's other papers that sort of get pretty much the same results in sort of different ways. So that's a bit of a theoretical mystery, but which I think there's a lot to bring to the table here from the applied math community, as well as from the statistical physics community, which in the 90s was very interested in this problem and sort of dropped out, but now they're coming back to it. So I think it's a fascinating set of developments. So backpropagation is just a practical application of chain rule for multivariate functions essentially, and it says if you want to compute the gradient of some objective function with respect to some variables, you just multiply the Jacobians of all of those boxes with respect to their inputs and parameters going backwards in the flow of computation. Now, this concept is surprisingly powerful. I'm sure a lot of you have used automatic differentiations in the past, and this is basically just like automatic differentiation. And in fact, the root of that algorithm can be traced back to classical work in optimal control in the 50s and 60s, where people use the Kelly-Bryson algorithm or the Pontryagin extremum principle, which basically for optimal control treats this problem of kind of a stack of functional modules that you have to compute gradients over. This is called the adjoint state model in optimal control. So the idea is very old. Of course, chain rule even in multi-dimension is very old. But the realization that you can use this to train the system through gradient descent actually did not really pop up until the 1980s. So that said, people have sort of generalized this concept. The type of architectures that people use nowadays are not just chains of linear and of alternated linear and nonlinear pointwise nonlinearities. It's more, there are more programs now. So the type of deep learning systems, the modern ones, are basically it consists in writing a program, a function, using a framework like PyTorch or TensorFlow, let's say PyTorch. And what the system gives you for free is the ability to compute the gradient of the output of that function with respect to sort of pretty much anything that goes on inside. And so this is a very, very powerful concept, which is sort of a generalization of automatic differentiation, if you want. And it's very flexible, and it runs on GPUs in parallel and all that stuff. So because there's been a huge demand for this. And so you can basically write your model, writing it as basically a Python program, and automatically you get to differentiate this with respect to any variable you want. And so that can be used for machine learning, can be used for optimal control, it can be used for numerical analysis. It's becoming a tool that a lot of communities now are using because of such interest in deep learning. So that has come to be known as differentiable programming. You can think of this more than just deep learning. It's programming in such a way that there is support for automatic differentiation in your programming language. Okay, so of course, very often you have to put some structure into the architecture of the network for it to process certain types of data appropriately. And there is the idea of convolutional net that my name is attached to, which basically replaces the full matrix of the linear operations by convolutions, which are another type of linear operators with fewer parameters. So basically each layer is a filter bank essentially. And then you have pointwise nonlinearity, and then there's another kind of operation called pooling, which basically is subsampling with some aggregation rule, which could be an average or an LP norm or a max. It's most of the time now it's called a max. The root of the idea of this goes back to classic work in neuroscience by Huber and Wiesel from Nobel Prize winning on the architecture of the visual cortex. And there really was inspiration from neuroscience. Even though you can sort of post hoc justify mathematically the reason for why this should be done this way. So convnets have been incredibly successful for a lot of applications. Every single automated vision systems for cars today, that keeps in lane and detects pedestrians and brakes automatically is based on convolutional nets. Most speech recognition systems are based on convolutional nets. Most new medical image analysis systems and image restoration systems are based on convolutional nets. So there is a huge amount of applications for this that have been deployed over the last few years, and the results in computer vision are just amazing. Now, back in 2012, people could sort of barely, with the best systems, recognize the dominant object in an image with far from perfect reliability. And then what we can do is basically train those neural nets to essentially label every pixel in an image with the object that it belongs to, right? So all those pixels are labeled as a person. This one is a bicycle. The bottle at the bottom here is detected. That's another person, etc. The persons are included but are still detected. And this is the idea of panoptic segmentation, where not just objects but also background areas are labeled like tree, sky, road, etc. And this works really well with hundreds of categories, sometimes thousands. Simultaneously, you can do post-estimation of bodies, and all of those basically use the same trunk, the same backbone for the neural net, with sort of different heads that produce the different results. So Facebook has a system like this called Detectron, which is open source, so you can just download it and play with it. It's pre-trained. You can train it if you want. Of course, it's been very successful in medical image analysis, and I think the use of ConvNet in medical image analysis is so promising that it's basically dominates a lot of current conferences on medical imaging. Those networks use a very interesting architecture that is sometimes called UNet, which includes a convolutional net that sort of represents images hierarchically by progressively reducing the spatial resolution and increasing the number of feature types. And then there is sort of a converse architecture, which you could call a deconvolutional net, that sort of regenerates an image of the same resolution as the input. And this is the kind of thing you want to use for image segmentation at high resolution, and like in the case of medical imaging, for example. These are pictures from a collaboration between Facebook AI Research and NYU on kind of speeding up the data collection for MRI data, where you can sort of restore the image with a fourth of the data that would normally be necessary for the full resolution image. So a lot of applications of deep learning and convolutional nets that pop up every day, but I think the ones that people will be more familiar with is for autonomous driving or semi-autonomous driving or driving assistance and medical imaging. Of course, it's already used a lot in online services for content filtering and things of that type. People tell me that according to some statistics, the automated emergency braking systems that are now mounted in every car in Europe as kind of a standard feature, it's kind of mandated by the government in certain countries, reduce the number of collisions by 40%, and that's enormous, which means deep learning and convolutional nets save lives. Same for medical imaging. Now, a very interesting development that some of you may be aware of is the fact that you can define convolutions on graphs. So if your data does not come to you in the form of a sort of regular array through 2D, 1D, 2D, 3D, 4D, if it comes to you in the form of a function on a graph, you can still define convolutions on graphs. So the idea is a convolution, of course, is a diagonal operator in Fourier space. So if you can compute a Fourier transform of your signal, then in the Fourier space, you just do a pointwise multiplication with the Fourier transform of a convolution kernel, and then do the inverse transform, and you've done a convolution. Now, you can define the Fourier transform of a function on a graph, and that basically consists in transforming the function on the graph into the eigenspace of the graph Laplacian. When I talk about this to computer scientists, I have to explain what all of this is, but in applied math, a lot of people know what this means. And so you can define this on just about any network, but of course it's very expensive because there is no equivalent of FFT for irregular graphs. So there's a lot of work on what's called geometric deep learning or graph neural nets that consist in sort of finding efficient ways to do the equivalent of convolutions on functions on irregular graphs, essentially. Sometimes even dynamic graphs. So graphs that, you have regular graphs in which you use standard convnets. You have irregular graphs with a fixed structure in which you can use those spectral convolutional nets. And then you have irregular graph whose structure changes with any new piece of data. So for example, if you want to represent a molecule as a graph, a new molecule will have a new graph. So your network needs to be able to digest graphs of varying structure. And that's entirely possible to define. Last year, or a couple of years ago, I co-organized a workshop at IPAM on new deep learning techniques, and there's a number of talks on this topic. If you really are interested in this, I recommend a series of talks by, recent talks by Xavier Bresson, who really has given wonderful lectures about this, as well as a recent blog post by Michael Bronstein from Imperial College, which I think is on Towards Data Science blog. Now, again, I think relevant to the applied math community is that people are starting to use convolutional nets as a way to compute efficiently approximate solutions of PDEs. So a PDE solver, an integrator is basically, the state of your system at time t plus 1 is the state of the system at time t plus the time increment times some function of the previous state. And you could think of the G function here as being a convolutional net. Very often the interactions are local in a PDE. And so you could think of this as the G function as some sort of convolutional net. And the question people are asking is, can I increase the size of the grid that I use to solve my PDE, and both spatial and temporal, and get the same result, not by actually solving the PDE, but by training a neural net to basically predict the result of the integration for several time steps with a coarser grain. And this seems like a free lunch, but it works. And so people are using this for things like lattice QCD in physics, for fluid dynamics, predicting the hydrodynamical properties of solids, for example, and perhaps optimizing them through gradient descent. And for cosmology, astrophysics, there's a very interesting work that I'll mention in a bit. Now, sometimes those grids are irregular. So we're back to this idea of using graph convolutional nets where your grid being irregular, you sort of have to deal with the irregularity of it. So that's an example of a paper that appeared a little while ago in PNAS by a group from the Flatiron Institute in New York. And they're interested in sort of simulating the early moments of the universe at the scale of the universe, and it's essentially impractical. So what they do is they train a convolutional net on the subdomain by just running the the equation that they know how to solve, but on a relatively small domain that generates training samples. And with this result, they train a convolutional net, which is actually one of those UNet architectures that was used for image segmentation. They train one of those neural nets to predict the result of the integration for several time steps, and only using information from coarser grain. And once they have the system, it's pretty efficient to run. So now they can run a simulation at the full scale of the entire universe and get some results that seem qualitatively interesting. There's a lot of really interesting work in this, which I find really fascinating. So this is sort of learning to integrate. So this is the use of graph neural nets for analyzing high energy physics experiments. Okay, so now a big puzzle. Okay, we're still far with our learning methods from reproducing the type of learning that we observe in animals and humans. And the question is, how is it that humans and animals learn so quickly? And I think it's really a very, very important question, because we need to be able to get machines to learn to, let's say, drive a car without running in simulations for millions of hours. We need to have machines that are really robust for performing computer vision or natural language understanding. We need machines to have some level of common sense to know how the world works, basically learning by observation. And that's the trick. The humans and animals seem to learn by observation without being trained to a particular task, but basically to learn to understand the world, right? So babies around the age of 2 months, learn concepts like object permanence. The fact that I can hold an object, but if I hide it behind me, it's still there. And babies learn this really quickly. They learn whether objects can kind of stay stable or will fall, and they learn things like gravity around 9 months. So if you show a 6-month baby an object that seems to float in the air, they're not surprised. But if you show that to a 10-month baby, the baby will look at it like the world is crumbling, a little bit like this little girl here. And the reason is that in the meantime, around 9 months, babies learn that objects are not supported are supposed to fall. Now, nobody tells them that. Nobody gives them the name of anything. They just learn this by observation. And they possibly learn this by sort of training themselves to predict, okay? So there is this hypothesis that's been around for a very long time, which is that what the brain essentially does is it trains itself to predict all the stuff that it cannot currently observe, and that it may be able to observe by waiting or by moving So when I move a little bit, objects kind of move in different ways. And so the best way to explain how my view of the world changes when I move my head is that the world is three-dimensional. I don't need my brain to be hardwired to know that the world is three-dimensional. If I move my head and I predict what the world is going to look like, I will have to infer the fact that the world is three-dimensional. That's the best explanation for it. My guess is that or my slogan, if you want, is that the next revolution in machine learning and AI will not be supervised. It will not be reinforced either, in the sense that, there is this mode of learning called reinforcement learning. It's even more inefficient than supervised learning in many ways, but I'm not going to go into this very much. Deep learning works well for perception as long as you have data. Deep reinforcement learning works well for action generation, but you need way too many interactions, which is why it basically only works for games where you can simulate the world. It doesn't really work in the real world. If you want to train like a robot arm to do something, you can do this to some extent by sort of transferring simulation to the real world, but it still takes the equivalent of tens of thousands of years of training in simulation for a system to learn to manipulate an object, for example. So I think there's really three challenges that the sort of machine learning, AI, deep learning community should strive to solve. The first one is learning with fewer label samples or fewer trials. And what I'm going to propose here is the idea of self-supervised learning. The second one is learning to reason. So essentially, all the classical deep learning systems compute their output by just propagating through a bunch of layers. But a lot of what we do as humans and a lot of what some animals do is sort of more reflective, right? You kind of think about something before doing it. And that requires sort of, satisfying a set of constraints. And so this is a view of reasoning that basically comes down to optimizing a function, right? The way you reason is by satisfying a set of constraints. You can measure the evaluation of those constraints as a set of, as an objective function, an energy function if you want, and you sort of minimize that energy function while you do inference. So reasoning might be optimization the same way learning is optimization. And then there's a third problem, which I'm not going to say anything about because I have no idea how to solve it. Okay, so what is self-supervised learning? Self-supervised learning is the idea of filling the blanks. I was giving you the examples of babies kind of learning to predict what's going to happen in the world by observation. And this is really the idea of self-supervised learning. Take a piece of video, show a piece of video to the system and ask it to predict what's going to happen next. Or take a piece of text, remove some of the words in the middle of the text and ask the system to predict the words that are missing. Or, I don't know, remove the top of an image and ask the system to predict the missing part of the image. So that's the idea of self-supervised learning. Pretend there is a part of the input you don't know and predict that. Now, there are two kinds of it. One kind where you know in advance which part is going to be missing, and it's always going to be the same one, like video prediction. And another one where you never know which one it will be. That's slightly different. So there's two uses really for self-supervised learning. The first one is learning hierarchical representations of the world, where self-supervised learning basically is a pre-training that precedes a phase of supervised or reinforcement learning that will train the machine to actually do a task, whereas the pre-training just trains it to represent the world. And the nice thing about this is that it doesn't require any label data, so you can use basically as much data as you want. It's essentially free. And then the second one is to learn predictive models of the world, which would be very useful for model predictive control and for control in general. So the big technical question we have to solve here, and this is again a question to the applied math community, is how do we represent uncertainty and multimodality in the prediction? So here's the problem. The problem is, if you're looking at me right now, giving this talk, and the next thing I could do is move my head to the right or move my head to the left, right? So let's say you train a system with initial segments of video of me talking, and you stop the video at some point, and you ask the system what's going to happen next. The system may have no way of predicting whether I'm going to say this or move my head to the right or to the left, which word I'm going to say, how I'm going to move my lips, etc. So there is necessarily a necessity of representing uncertainty in the prediction. You cannot make a point prediction because the best thing the system will do if you train a predictive system like this with least square is that it will produce an average of all the possible features that can happen, and so, which is not a good prediction, right? It's going to be a blurry version overlapping versions of my face, right? So, so how do you represent uncertainty? So of course, if you're a machine learning a person or a probabilist, the first thing you say, or statistician, you say, well, you know, don't learn a point, learn a distribution. And this works in certain cases. So, but it doesn't work in continuous spaces, because if you want to predict frames in a video, we basically have no way of representing good distributions in the space of all video frames. This is a problem that we just don't know how to do it. And all the things that people have tried basically don't work very well. So, so one way to deal with this problem is to abandon the idea that we have to estimate distributions, and to basically focus on estimating level sets of a distribution, or representing the log of a distribution in an unnormalized manner by an energy function. So this is my favorite approach, which I call energy-based models, and a lot of people have been, you know, using this or proposing this in the past. So this is not necessarily my own invention, but I've been pushing this a lot. So an energy-based model is an energy function f of xy, where x is an observed variable and y is a variable you want to predict, and it's scalar valued, and the scalar value that comes out of it is going to be low if x and y are compatible with each other. So if y is a good prediction for x, say the good prediction for the future video where x is the initial segment, and the output value is going to be higher if y is not a good continuation for x, not a good completion of x, if you want. So the inference process in an energy-based model, which is computing the output, consists in finding a y, which there may be multiple, that minimizes f of xy. Okay, that produces a low value for f of xy, and there might be several. And of course, there are several energy functions that will give you the same y's. Okay, there are two examples here at the bottom, two different energy functions that give you the same result. You know, this is x, this is y here. So more generally, you will have a space. It would be a space of x and y, or just a space of y if your system is unconditional, doesn't have an observation. And your data points are those black dots. And what you need to learn when you train an energy-based model is the function represented by those contours here that takes low value on the data and higher values outside. If this function is continuous, differentiable, relatively smooth, you can use gradient descent to do inference, right? So I give you an x, and you can find by gradient descent the value of y that will minimize your energy. So this is basically replacing a feed-forward function of a neural net by an implicit function, really. And in fact, you can recast a lot of classical learning algorithms in terms of sort of energy-based models. So things like, let's say, k-means, for example. So this is running k-means on a set of samples that are drawn from this little ellipse here in 2 dimensions. And what is being plotted here is the energy function, the energy surface after k-means has been trained. So each of those black areas are basically energy wells centered around prototypes. But the way to represent multimodality in an energy-based model is probably to do something like is shown here, where you take your x variable, you run it through a neural net or some parameterized function that produces a representation of the observation that are called h. And then you can run this through a decoder that makes a prediction, and you can measure the discrepancy, the error, the distance between the prediction you are given, the desired output you are given, and the prediction that the system produces y bar. Now, if there are multiple y's that would be compatible with this x, you're only seeing one sample here. What you want is this to represent some sort of manifold. It may not be a manifold, it could be a set of some kind of all the possible plausible predictions. And the way to parameterize this manifold is through a latent variable. So you have a latent variable z here that goes also into the decoder. You can vary this latent variable over a set. And as you vary this latent variable over a set, your prediction varies over this manifold. Now, again, that's an energy-based model. And what you can do is minimize with respect to z. So if I give you an x and a y, and I ask you what's the energy of this pair of xy, what you have to do is find the value of z that minimizes the prediction error. You immediately see a problem, which is that if z has too much capacity, let's imagine that z has the same dimension as y, then there's always going to be a z that for any y is going to produce essentially a zero reconstruction error. Imagine that z is the same dimension as y, and the decoder happens to learn the identity function, or something similar to this. Then for any y, there's going to be a z that's going to make the reconstruction error, the prediction error, 0. And so obviously that's not a good model. If your model ignores the input data and gives you zero energy everywhere, you need a way to ensure that the energy is small or zero on the data points, but you need a way to ensure that it's higher outside the data points. And you have two options for doing this. One is called contrastive methods, and the other one is called architectural methods. So the architectural methods consist in essentially limiting the information capacity of Z by either minimizing its dimension or the rank of the various values of Z over the training set, or by making it sparse, or by making it noisy. I mean, there's various ways to do this, but that's essentially what it comes down to. You have to limit the capacity, information capacity of Z somehow. Now, inference, when you have a latent variable model like this with Z, it can be done in two ways. The one I explained is minimizing with respect to Z to eliminate it. So this is this. Another way, if you're a probabilist, is marginalize over Z, and that comes down to basically computing what physicists call a free energy, which is this little formula here, where beta is some arbitrary positive parameter. And this formula here, which is basically a sort of integration over possible values of Z, reduces to the one at the top here when beta goes to infinity, which is the zero temperature limit in physics. So latent variable models, I mean, this is a small illustration of a latent variable model where imagine that your data manifold is an ellipse, and then the latent variable would be the angle of a point on the ellipse. And then when I give you a data point y, the energy of that point is the distance to the closest point on the ellipse. So I have to minimize that distance with respect to the latent variable, which is the angle, to find the energy, right? Very simple. But of course, in reality, we don't have this manifold. We have to learn it. Okay, so how do we train an energy-based model? Two methods, as I said, contrastive methods. And contrastive methods consist in taking a data point, pushing down on it, and then taking a point outside and pushing up on it, or taking a bunch of points outside the data manifold and pushing up on them. And that actually works quite well in the context of image and speech recognition at the moment, but it's extremely expensive computationally because in high dimensional spaces, you have to push up on lots and lots and lots of different places. But that's a somewhat successful category of method that's very popular at the moment in computer vision and speech recognition. And then there are this other class, which I think in the long run will probably win out, but at the moment they're not actually working very well. Those regularized architectural methods that consist in explicitly regularizing the capacity of the latent variable so that you limit the information capacity of it. So this is a bit of an eye chart, but it basically lists a lot of classical machine learning algorithms as to whether they are contrastive or regularized or architectural. So things like metric learning Siamese networks, which I'm going to talk about in a minute, are contrastive methods. Adversarial methods like GANs are this type as well. Denoising autoencoders and masked autoencoder that are incredibly successful in the context of natural language processing are also contrastive. So those really work really well. Those don't work nearly as well, but in my opinion, in the long run, they're more promising. And this connects with a lot of things artifacts that the applied math community has been obsessed with for a very long time. Think like sparse coding, sparse modeling, ISTA and various things like that. And then things that are more kind of modern in the deep learning community, like variational autoencoders, sparse autoencoders, VQVAE, and things like this. I'm not gonna talk about the rest. Let me skip this. In contrastive methods, there's various ways to define objective functions. And basically the basic design principle for a good objective function is that your objective function will have a term that's going to push down on the energy of a data point, x, y. And it's going to have another term that's going to push up on the energy of some other point that somehow has been generated to be outside the manifold of data. So this is an example of a margin loss, but there is like a whole bunch of those losses that people have used in various contexts, mostly not in the context of self-supervised learning, mostly in supervised learning. But you have a kind of a wide array of possible objective functions. If you insist on estimating densities with your system, so if you insist that your energy function be the logarithm of some distribution, then the only objective function you can use is the negative log likelihood of the data under your model, which is basically a particular type of objective function that has a term that pushes down on the energy of data points, and then a horrible intractable integral that attempts to push up on the energy of every point, including the data points, but with a smaller force. And so probabilistic approaches basically force you to use a particular type of loss function that happens to have a completely intractable term in it. which is why I'm a big advocate of those energy-based models. It gives you more flexibility in the objective function, and you might be able to eschew the issues due to those normalization. Now, something that's really popular at the moment is those so-called contrastive methods, which are really sort of an application of what's called Siamese networks. And I'm not going to go into the details of what the objective function is, but, and I don't seem to, and here is the slide. So people call this contrastive embedding. And the way you do this is that you take a sample, you distort the sample in some way that does not change its nature. And those are this is your pair X and Y. You run those two images through two identical neural nets. They both produce an H, a representation. Okay, and then you compare those two representations. So those are vectors. You just compare them with some distance, say Euclidean distance, or cosine similarity, so that you normalize the norms. And what you do is that when the pair of images are semantically identical, then you force those two vectors to be as close to each other as possible. That's one term in your cost. And then you have a contrastive term that where you pick a random sample from your data set, or maybe not a random sample, but a sample that you know is different. And you feed those two images, and then you force those two vectors to basically move away from each other. You can use one of those losses I was talking about earlier. People use currently what's called this NCE, noise contrastive estimation, which is some normalized exponential of those similarities. This works really well. So the idea goes back a long time, a paper of mine from '93, where we used this for signature verification. And this sort of more recent work I did with my students in the mid-2000s that was largely ignored. And more recently, those methods have become extremely successful for learning features in images. In fact, there is a more recent paper from DeepMind here that uses a somewhat similar idea, although a little different, which works even better. And there's a whole crop of papers that are being prepared that are popping up on archives that use those methods nowadays. Let me back up a little bit. So one thing that's been incredibly successful is contrastive methods in the form of denoising autoencoder. So what is a denoising autoencoder? You take a piece of data Y, let's say a piece of text or an image, let's say a piece of text, you corrupt it in some way. So you remove some of the information, or you corrupt it. In the case of a text, you would remove some of the words and replace them by a blank marker. And then you run this through some big neural net, and you train this neural net. In the case of NLP, this neural net is usually what's called a transformer, which is a particular type of architecture. And then you minimize the reconstruction error. So you basically train the system to predict the clean version of the input, only using the corrupted version where some of the input has been masked. Okay, so basically training the system to predict the words that are missing in your text. In the process of doing so, the system learns a representation of text that actually contains all the semantic and syntactic information about text. So if it sees a sentence like the blank in the house chases the mouse, it will easily infer that the missing word is cat, because it's seen similar examples before. And what it produces is a probability distribution for every missing word. And that probability distribution is over all the possible words in the dictionary. So self-supervised learning in the context of text works amazingly well. I mean, this method of pre-training a natural language understanding system has now become universal. The basic idea of it, the basic form of this, the special form of this has come up about 2.5 years ago, and it completely revolutionized the way people do NLP. And now it's used absolutely everywhere. And those networks are gigantic. There are hundreds of billions of parameters, sometimes at least billions of parameters. So incredibly successful use of self-supervised learning there. You can have dialogue systems now that almost sound human. Some researchers at Facebook AI Research in Paris, Guillaume Lample and François Charton, have actually trained one of those systems to, as if it were language translation, to actually solve differential equations. So symbolically, this is not numerically, this is symbolically, right? So you give an equation like this, it's represented as a string, which is turned into kind of a tree representation in Polish notation to the input of the system. So it sees this really as a text. And then you train it by generating example backwards. You train it to just integrate this differential equations very simply. And it works for computing integrals symbolically, solving differential equations, first order and second order. It works better than whatever MATLAB, Maple, and Mathematica gives you in many cases, which is amazing. They have a similar system now that is trying to translate a program from one language to another, substituting the appropriate idioms and function calls and everything. It's frankly completely amazing that it works at all, but it does. Okay, let me skip this in the interest of time. So connecting this with things that people know in applied math is this idea of sparse coding. Okay, so here this is sparse coding, sparse modeling, formulated in terms of those energy-based models. So you have a latent variable. It's regularized by some sort of L1 norm in the case of sparse coding. The decoder is a linear function just multiplying by a matrix. You have a reconstruction, and the reconstruction error is just a quadratic distance. And the inference process, of course, consists in finding the value of z that minimizes the reconstruction error. And that's basically sparse coding. Sparse modeling consists in learning this matrix by gradient descent under some constraints on the norm. Now, there is something interesting about this, a twist that has appeared over the last 10 years or so, which is sparse auto-encoders, and what people have now come to call amortized inference. So instead of doing the inference of this variable by doing the ISTA algorithm that optimizes this function every time you have a new y, what you do is that you train a neural net to predict what the solution of that optimization problem is going to be. So instead of solving an optimization problem, you train a neural net to solve that optimization problem. And you hope that this neural net will give you kind of a good approximate solution, which you might refine or not at the end. And this form of what's called regularized autoencoder is very powerful. So you can think of this latent variable as being optimized or marginalized over, and you can think of this guy as kind of predicting the optimal value of the latent variable. There's a form of this called variational autoencoder, which I'm not going to go into, where basically the z's are not points, but they are like little Gaussian fuzzy balls. So sparse coding works. You train sparse coding on MNIST, and you get columns of the decoding matrix that look like parts of characters. And if you train on natural image patches, it learns really quickly that image patches can be approximated by a weighted sum of a small number of edges, oriented edges. And you can actually push the analogy even further. So this is a system that I call LISTA, Learning Iterative Shrinkage and Thresholding Algorithm, which consists in basically viewing the ISTA algorithm as, which is the optimization algorithm to solve this L1, L2 problem, as a recurrent neural net. And you're going to train the matrices in that recurrent neural net to give you a good approximation to the optimization problem as fast as possible. And it's amazing, but it works. And it seems like a free lunch. Like, why would a trained system give you a better, faster approximate solution than actually running the optimization algorithm in the first place? And the reason is that this system is only trained to solve the problem for certain types of inputs. It's trained, for example, with image patches or with audio signals. It's not trained to solve the problem for any random signal, which of course the full algorithm can do. Okay, so let me skip ahead. So there's sort of various ways of training the systems, but I want to come to one particular one, which is using those kind of latent variable models to do video prediction, and to do so in ways that can help, for example, self-driving systems. So let's say you have a bird's eye view of your car surrounded by other cars. The green cars are other cars around you, you are the blue car. And you observe what the cars around you have been doing so far. And what you'd like to do is being able to predict what cars around you are going to do, so you can plan a good trajectory ahead and avoid accidents. So you can train one of those energy-based models to kind of make the prediction, and the prediction will be multimodal. So these are examples. I hope you can see the video. If you don't have a latent variable, you just make a point prediction. You get the blurry prediction that you see on the second column. But if you do use a latent variable, and you change the way you sample the latent variable, you get 4 different types of predictions here that are shown on the 4 columns on the left. The one on the right, I'm sorry. On the left is just a recorded training sample that actually occurs. So you can have multimodality with these latent variable models. And this is very important if you want to do model predictive control, which I'm sure many of you are familiar with. So you have a forward model of the world that predicts what the next state of the world is going to be as the function of the previous state, the action you're taking, and perhaps some latent variable that you have to draw at random. Okay, and if you can unroll this model in time, and you can measure an objective function, C of S, at every time step, you could imagine by gradient descent optimizing a sequence of actions that will minimize your cost, right? This is classical model predictive control. And of course, all of those is differentiable. Your model has been trained in advance, so you can just do this by automatic differentiation using the same tools that we use to train neural nets. Now, another thing you can do that's more efficient is that instead of inferring a sequence of action, you use the gradient of the cost over the sequence with respect to the action to train a policy, what's called a policy network. So it's a network that takes the state at the previous time step and tries to predict the action. So again, it's one of those types of amortized inference that I was telling you about earlier. And if you train the system to drive itself in the context of what I showed, it actually works quite well. This is a trick you have to use to kind of prevent the system from going into parts of the space that are where the predictions are unreliable. But it works pretty well. So this is an example of the blue car driving itself. The little white dot indicates whether it accelerates, whether it brakes, or whether it turns. And you have to realize that here, the green cars are recorded. The blue car is invisible to them because it's a new car that we just put in this recorded video. And so it has to basically learn to avoid the other cars, avoid getting squeezed. And it works okay. Right, so conclusions, conjectures, and open questions. Self-supervised learning is learning dependencies. Reasoning is minimizing energies, basically inferring latent variables. You could think of it this way. I didn't talk much about this, but this is what it comes down to. The main obstacles we have to face is how to properly represent uncertainty. And my recommendation here is to abandon the idea that we need to learn distributions. And learning energies is simpler mathematically and in theory. So I'm proposing to use energy-based models. And there are contrastive methods and regularized latent variable methods. And my money at the moment is on regularized latent variable energy-based models, even though the contrastive form is actually, as of today, much more efficient. Now, beyond this, could energy-based self-supervised learning be the basis for machines to acquire common sense, basically by learning how the world works by watching video and not interacting much like maybe humans and animals? I think it's an interesting question. I hope the answer to that question is yes, but I really don't know. And just as a side note, a lot of people are talking about artificial general intelligence and are kind of hoping that by scaling either supervised or reinforcement learning methods that we currently have with bigger hardware and more data, we'll reach something like human level intelligence. I think this is completely hopeless. I think to reach anywhere close to even cat level intelligence, we'll need to go through this type of learning. We're not going to get there just with reinforcement learning or supervised learning. There's been a lot of discussions also about deep learning, whether it's an engineering science or a natural science, whether it's actually a science or more like alchemy. And the interesting thing about deep learning is that it's an engineering artifact that we need to study and that we don't completely understand. And it's not because we don't understand it that we should not use it, right? Because in the history of technology and science, a lot of artifacts like the telescope, the steam engine, electromagnet, the airplane, etc., have appeared before people actually had the theory to explain how they work, right? The theory was actually developed as a consequence of those artifacts being developed and being useful. And so it motivated theorists to kind of really understand what this was. I think that's really the history. So we're in a kind of similar situation here where we have an artifact, deep learning systems, but we don't really have sort of a general theory that explain why they work. So we are like, people who built steam engines in the early 19th century or late 18th century. They had to wait for roughly 100 years for thermodynamics to really explain the limits of it and why it works. So the goal of my career is basically to figure out what is the equivalent of thermodynamics for machine intelligence or for intelligence in general. Thank you very much.
Yeah, thank you very much for a fascinating lecture. And so now we come to the question and answer session, and there are a lot of questions which came in. So one question is, for instance, by Bernhard Gottmeier. He asked, currently the weakness of reinforcement learning are strategic decisions because they lead to delayed rewards. Can you give some input about how to solve this problem?
Right, so, okay, there's 3 problems in reinforcement learning. The first problem is your objective is not known. It's not a module in your program. It's not a differentiable function whose derivative you know. It's something you can only measure by taking an action in the world and then observing the result from the world. So the world is going to give you a scalar value, basically, that tells you the action you took was good or bad. And it's not going to give you that value every time. It's going to give it to you once in a while. Okay, so basically it comes down to trial and errors. The second problem is that the action you take will determine the sample you see next. Okay, and so you learn to ride a bike, and if you do something, you're going to fall. That will determine what sample you learn from next. And so you cannot make the usual hypothesis in machine learning theory, which is independence of samples, right? You don't have independent samples. So those are the two main problems. And the third main problem I already sort of alluded to, which is the fact that the environments only gives you back a single scalar. And so because it gives you a single scalar, it's horribly inefficient. You need many trials to learn anything, unless you already have a good representation of the world. So one might ask, what is it that allows humans to learn to drive a car in about 20 hours of training without causing any accident, mostly? Whereas if you were to train some of the best reinforcement learning systems at the moment, at least the pure ones that are model free, it would take millions of hours of training, which of course you could only do in simulations. And the car would destroy itself, hundreds of thousands of times, if not million. So the difference is that humans have this predictive model of the world in their head, and they also have a good idea of the objective function. And because this objective function is computed by their brain, it's differentiable. I mean, they know it, right? So you could imagine some way of estimating gradients that don't imply interacting in the world. And that's pretty much what I showed in my little example of a self-driving car. It's not reinforcement learning there. Nothing is reinforcement learning because everything is differentiable, everything is known, and the system has a complete model of the world, which is itself differentiable, which it learned through observation, through self-supervised learning. So what allows us to learn to drive a car quickly is that we know that if we drive next to a cliff next to us, if we turn the wheel to the right, the car is going to run off the cliff and nothing good is going to come out of it, right? Our model of the physics and our model of the objective function, which is that we shouldn't fall down a cliff, is such that we don't need to try. We know that the result is going to be bad, right? So this idea of learning predictive models, crucially, is what was going to bring the sort of a new, the next revolution in reinforcement learning as well. Now, the problem is that it's the same problem that we had with neural nets way back, which is that from the theoretical point of view, it's very hard to prove that model-based reinforcement learning works better than model-free reinforcement learning. In fact, you can prove the opposite. So in theory, model-based is worse than model-free. But in practice, it learns way faster if you do it right. So the proper way to do this is not clear. But it's the future, there's no question.
Thank you. So another question is about energy-based models. And the question is, energy-based models look like free energy minimization from chemistry and material science to simulate materials properties. I mean, are these ideas from both fields? Do they use ideas from the other field? So can you comment on that connection?
Yeah, absolutely. I mean, I use the same symbols as in statistical physics, basically, right? So the -1 over beta log integral e to the minus beta the energy, that's a free energy. I mean, up to the -1 over beta. But this is like there's the very famous equation in thermodynamics, which is the free energy is equal to the average energy minus the temperature times the entropy. And this term that I talk about here is the minus temperature times the entropy. So I mean, basically it's the free energy, but divided by the temperature, multiplied by the temperature. I mean, clearly the math is the same. People talk about variational inference, which is completely borrowed from statistical physics. When they don't use variational inference, they use Monte Carlo and Markov-Chain Monte Carlo inference, which is also derived from physics. So yes, the math is the same. The concepts are the same. Some people in machine learning actually get annoyed by me because I stick to the notation of physics, and people in machine learning, like to talk about objectives that you maximize rather than minimize. So and they always prefer to write distributions instead of energies. So so they get annoyed by me because of that. But yes, it's the same math.
Mm-hmm. So another question is by Gantavi Bhatt. He asked, in many works, people tend to apply contrastive loss in the latent spaces. Can you comment on when the model trained with loss applied in the original space will surpass the contrastive loss applied in the latent space, or in general, what are the weaknesses of contrastive learning paradigm?
Right. So I don't know if I can go back to the slide. I'll try, but it may take a little while. Yeah, so I mean, the contrastive, the Siamese network, the sort of standard form of contrastive learning that people use at the moment actually does contrastive learning in the representation. But there's a slide that I skipped that I want to go to, if I can, which is another example. So this is another way of learning, training a latent variable energy-based model to do prediction, which does not require contrastive terms. And so this is a thing where you try to extract a representation of a frame. So let's say those are video frames, right? So you look at yt minus 1 yt, and you're trying to predict the next frame, yt plus 1. And one thing you could do is basically train an auto-encoder to encode this frame yt of 1 and use the same auto-encoder to encode the next frame. So what you get are two codes, h, for the two frames, and then have an internal model that you train simultaneously that attempts to predict what the next h is going to be for the next frame. And then you decode and minimize the reconstruction error, I mean the prediction error for the next frame. So ignore the bottom part of this at the moment. Okay, so this is sort of a predictive model. It doesn't require any contrastive learning or anything. And the reason it doesn't require any contrastive learning is because you force the H representation here to contain all the information about the input, because you force it to reconstruct the input. And so you know that no information is going to get lost in the encoding of y into h because you force the reconstruction. That's an alternative to the contrastive term that tries to make sure that representations are different for different inputs. Here they must be different because the system must be able to reconstruct the input. So you have those representations, and then you train a third network, a kind of a predictor network, if you want, to predict the representation of the next frame. Okay, but it's quite possible that there are a lot of things in the prediction that are not predictable, that the information is insufficient in the past to predict the future. As I said, the world is not entirely predictable. There's some stochasticity to it. And so what you could do is add a latent variable to this h that basically takes into account all the stuff that you cannot predict that may happen in the model. The diagram here is not completely accurate for this situation. I guess the situation is more akin to the one I showed for the driving system. And you can think of this encoder here as again, implementing this amortized inference idea of predicting the optimal value of the latent variable without having to do kind of inference. So yeah, I mean, I'm a big fan of this idea of eventually, essentially kind of forcing the system to do prediction in latent space. But I'm trying to eliminate the contrastive phase because it's too expensive computationally.
Yeah, thank you very much. So for the sake of time, I would now hand over again to Carola.
Thank you so much, Yann, for a really fascinating talk. I very much enjoyed it. And we had an amazing turnout in terms of participants, just to emphasize this. I think at some point we had more than 500 just here,
oh,
and
wow.
I'm sure there are many more on
well,
YouTube.
Thanks everyone for showing up. That's wonderful to hear.
So I'll just conclude this session by reminding everyone of our next and final plenary talk that will be given by Yuri Nesterov on Tuesday, this coming Tuesday, same time, on inexact accelerated high order proximal point methods. So until then, see you soon. Thank you.
Bye-bye. Thank you very much.